Test 1, 2, 3. Okay. Okay, good morning, everyone. Welcome you to SCI33205. This is the physics number 4. It is the section for M604, right? My voice may not seems to be as usual because there is a problem about the nose. Okay, okay, I will let you come here more and more so that I can inform you only once. We discussed the story about magnetic force on current carrying, right, on 29th of June, and I think on 8th of July you're gonna have the midterm exam, right? And the midterm exam will last until electric generator, which is very, very far from here, but I have provided the list of the link. You can watch all the lectures until we reach the last one, 26th lecture, okay, which was held last year, okay, to your elder classmate last year, right? Okay, what else? Okay, just choose or pick up only one. Okay, there might be a mixture between M604 and M605. Okay, just watch only how many times as you want, or how much time you have in order to watch or study yourself. Okay, if you have any problem, any question, just ask me. The last topic that the midterm exam will cover is electric generator in 26th lecture. Okay, please watch yourself. It might take 1 hour for each lecture. Okay, because last year it was new for me to have some devices. There might be some problem about devices and so on. The sound may not work perfectly, or there was internet connection problem because I didn't use the real fiber optic internet connection. Okay, now let's move to our story. I will go as much as we can. Otherwise, you need to start to watch the lecture in those videos.นะครับก็ให้ไปดูวิดีโอนะครับที่อยู่ในลิงก์ใน Google Classroom นะครับเนื่องจากว่าสอนไม่ทันนะครับคือถ้าสอนจริงเนี่ยสอนจริงนี่ห้องจริงนะมันจะเร็วกว่านะครับแต่ออนไลน์มันก็จะช้านะครับปีแรกนะครับไปได้เร็วนะครับสอนห้องจริงโอเคwe left at this formula right in I should watch what's going on with you in Zoom too, right? Okay, as you know, we have the formula, which is the product of Q, the charge, the velocity of any particle, right, in the magnetic flux density. And in this scenario, we have solar particles like electrons or positive charges, and because those particles may not have the same velocity or speed, they're gonna use the average value, which is the drift velocity, and it's denoted by V with subscript D. Okay, and B is the magnetic flux density. As usual, this is the absolute value of the shot, right? Whether it's positive or negative. And in this case, the copper wire, or the long straight copper wire, or the conductor, is arranged in rectangular, in normal direction to the direction of the magnetic flux density B. Okay, so the angle between the shot movement, or the velocity, and the magnetic flux density will be not exactly 90 degrees, right? So โอเคครับถ้าใช่นะครับอยู่ที่ YouTube ครับ YouTube ก็ได้ครับแล้วแต่คุณเลยครับรุ่นพี่คุณปีที่แล้วไม่ค่อยเข้ามาที่ซูมครับ604เข้ามาที่ซูมอยู่คนเดียวตอนหลังๆครับนอกนั้นไปอยู่ YouTube กันหมดครับขอว่า YouTube ภาพชัดกว่าครับถ้าอินเทอร์เน็ตคุณแรงๆครับเปิด 1080 นะครับภาพจะชัดมากครับซูมมันได้720ครับโอเค up to you I would try as best as I can. Okay. F here without the arrow above means the absolute value of the force, right? As usual, this is the scalar quantity. And once we substitute theta by 90 degrees, we're gonna get number 1, right? This is number 1, so we don't have to write it at all. It's nothing more, right? Charge is the value of the charge of the moving particle in Coulomb. Everything is denoted in SI unit system. Okay. The magnetic force. Okay, let n be any number integer, right? From 1 to until the last particles or the last charge, and if the conductor has a segment of the length L here, of the length L, we start from FQVB, right? For the n moving charge particle, we have absolute value of that charge particle, whether it's negative or positive. The drift velocity will be the same for every particle because this is the average value of the speed for all particles. Magnetic flux remain the same because it's assumed that it's uniform, and for all n particles that move, okay, with the same speed vd, we can see that the velocity could be computed by, let's say, it starts from here at time 0, and when it reaches L, we assume that it takes delta t second. So the velocity, the speed will be the distance, right? L divided by delta t, that the time that you have measured. So drift velocity will be L by delta t. Okay. Now let's consider the realistic situation. If you have the magnetic flux density like this, the vector is pointing. What does this mean then? The cross symbol, it means the magnetic field line is pointing into this paper, right? This plane, this lecture note. Okay, the magnetic field is directed onto this page, and this is the long straight copper wire, right? Once assume that we fix both ends of the conductor, and we have the conductor line or something like that to connect to the battery or something like that, so the current can move in this direction. Once there is no current moving, there's no charge moving through this conductor, there is no force at all. But once the charge moves through this conductor, right? The current is going in this way, and yes, you can use the right hand rule, right, to determine F is Q V cross B, right? So V is in this direction, right? And B is the magnetic flux density, which is pointing into this plane. So you rotate your four fingers from upward direction, up direction to the into this paper direction. So we get the force that points to this direction, right, to the left. That's why the conductor is bent a little bit to the left. But in the opposite way, if you let the current flow from the top to the bottom like this, okay, in the opposite direction, you have vector V downward like that, like this, right? The vector V is directed downward, but the magnetic field is remains the same, okay? Its direction is directed into this plane. So we rotate your forefinger. We rotate our four fingers from downward direction to into the plane direction. We get the force pointing to the right hand side. Okay, that's why the conductor is bent a little bit to the right. Okay, once there is no current, the conductor just stay in a straight way like this. Okay, there is no force acting on this conductor at all. But once there is current flowing, it depends on which direction. Okay, we have to use the right chain to determine the force, and because the conductor is fixed only at both ends, it can be flexible at any point. Okay, the force will happen from here to here. Okay, not above this and lower than this, because there is no magnetic flux at all. Okay, now let's consider the total amount of charge. If we have capital N charged particle that moves, right, we have the total amount of charge as the capital Q. Okay, capital Q is the summation of all charges. Okay, and as you know, the current is the flow rate of the charge, right? The rate means you have to divide something that you want to observe with respect to, you have to divide any quantity you want to observe by time, right? You observe the whole amount of the total amount of charge, which is capital Q, and the time that you observe is delta T, okay, from this starting point to the ending point. So the current will be charge per time of observation, so capital Q divided by delta T, okay. And now let's consider the induced force for each charged particle. Fn is QNVdB, right? That's what we have got before from equation 30. Okay, and force is the summation of all particles, right? In the same way, because we assume that the charge has the same polarity, whether it's positive or negative. Those are all the same, positive or negative. Okay, okay, this term summation of Qn is actually equal to the Q, right? The capital Q amount, and velocity is the length divided by delta T, the time of observation. Magnetic flux density remains the same, but if we move delta T to be here, we're gonna get Q by delta T. Q by delta T mean the current I, right? So the final result will be ILB. So that's why we get the total force that acts on the conductor will be F equal to ILB. All right, this formula. So the total force will be FILB, right? But if we have if we align the connector in a spatial way in any angle, like it's not right angle, it's not 90 degrees for any angle theta, this expression will be ILB sine theta, okay, because we project this is the origin of B, right? When we have to consider the magnetic flux density that is perpendicular to the charge moving, charge movement, right? This component, and this component, if this angle is phi, this component will be B sine theta. This one is B cosine, which is the parallel one. We consider only the component that is meaningful to us is B perpendicular, which is B sine phi. We don't pay attention to the B cosine phi because it has nothing to affect the force and so on to the chart here. Okay, so this one will be B perpendicular, and that's why we get ILB sine phi, okay, for any angular. And if you want to find the force direction, you can also use this one, okay. It lies in a similar way to FQV cross B, but this one is IL cross B. I is the current, okay, the current is constant. The current is constant, is scalar, is not a vector quantity. So L is the length vector of L is the length vector of the connector. So once the current flows in this way, vector L will be directed in this way. IL and B be this one, right? And that's why we get force upward here in the up direction. Okay, if you have the current flows in this way, this is the angle phi. We project vector L. We project the vector B to be here, right, perpendicular to the vector L, and that's why we get B sine phi. Okay, the force will be directed upward, okay, from vector L to vector B. Okay, you rotate your forefinger from this way to this one. Okay, you get thumb direction pointing upward. Okay, and if your magnetic flux density is directed this way to the negative x axis, and if the connector is still arranged in this way, you can see that the angle is greater than 90 degrees, right? And you rotate it from vector L to vector B, you get the induced force direction pointing downward like this by using the right hand rule. Okay. Let's consider this scenario. If we flip this conductor up to the opposite direction, and we would get the vector L this way, right? We rotate it from this one to this one, okay, to this vector, and we're gonna get the induced force pointing upward. Okay, don't rotate the vector L in this way. Okay, it's greater than 180. We will not rotate in that way. We rotate the vector L to vector B in the sense that the total angle is less than 180 degrees. Okay, and don't rotate your vector L in this way to vector B, and you get the induced force pointing downward. No, it's not the case. You have to rotate in the sense that the angle is less than 90 degrees or 180 degrees. Okay. The application of this magnetic force on current carrying conductor is like a speaker. Okay, we have the paper cone. Okay, in order to suppress the air. Okay, we hold this end of the cone to the frame of the speaker. Okay, and this one can move due to the current here. Okay, in the lower side, the current is moving into this plane, right? In the upper side, the current is going out of the plane. So once this is the solenoid actually. Let's say if you consider the upper direction here, these 3 connectors, it means you have the current flowing out of the paper, and vector V or vector L is pointing to us, right? From vector L to vector B, right? Because this is the north pole and we have 2 south poles here. The green lines will represent the magnetic flux or magnetic field line, right? Magnetic field line starts from the north pole to the south pole, right? There will be 2 directions for the magnetic field lines, this way, this way, this way, right? And also pointing upward from north to south. For the upper part here, we cross our fingers from the out of paper direction to the direction of the magnetic field upward, right? It's going to be that you can see that the induced force direction will be in this way, okay, from right to left. And also for the lower part, the current is moving into the page, right? You have the vector L pointing into this paper, this plane, and you have the vector B pointing downward. You rotate your forefinger, you can see that the induced force is gonna point to the left also, right? And once you change direction of the current, the paper cone can go this way, this way, this way. It depends on the frequency. It depends on your music or the voice of any speaker, okay? And that's why once the paper cone moves, okay, it's gonna compress the air, and the air will travel to our ears, and we can hear any music, any voice from the speaker. And this is the functionality of the speaker, okay, that borrows the theory of magnetic force on the current carrying conductor. Okay, but it's okay, you can see that it's worth to study something like this, but for us, in order to evaluate whether you understand the theory or not, we're gonna see the an example which is taken from book number 1, the world's lightest bird. Okay, you know that it's hummingbird, right? Yeah, from basic side, you know that hummingbird is very, very, very small. It's even smaller than the insect somehow, okay? The mass of the hummingbird is very light. Is only 1.6 gram, okay, very, very little. But the bird is different from the insect or bee or something like that, because they have their own bonds, right? Okay, they wanna build up the perch, okay, ก็คือที่จับนะครับให้นกจับนะครับ they want to build up the perch that is oriented to the right angles to the uniform magnetic field. Let's say that is the magnetic field around here, okay, and we don't know whether the direction of the magnetic field is pointing into this plane or out of this page, okay. The perch should be strong enough to support the perch and the bee hummingbird, okay, because there is 2 masses. The first thing is the mass caused by the perch itself, because the perch is made of copper. The copper has its own mass. The second one is that it should be able to support the mass caused by the hummingbird. So once the hummingbird stay on these perch, they want to build up these perch such that the perch and the bird will not fall down. So we use the magnetic force, okay, we didn't inherit to any base or any structure or any frame, okay, so that they use the electricity to hold the bird up, okay, to hold the bird up, to carry the bird And yes, the purse is 10 centimeter long. Okay, it's not so big. Okay, only 10 centimeters, and has a mass of 7 grams. Okay, it's even greater than the mass by hummingbird. And the purse contains a wire carrying a current I equal to 4 ampere. Okay, let's say the current moves from left to right with the amount of 4 amperes. And what are the direction and magnitude of the magnetic field in this scenario? That's the first. That's the only single question. Okay. You know that the force that acts onto these combined objects, the bird and the perch, is the force caused by the mass of the perch and the force caused by the mass of the hummingbird, right? It means the total weight of both materials, the birds and the perch. So W is the weight, which is the mass of the hummingbird and the mass of the perch, okay, multiplied by the gravitational acceleration on Earth, right? It's 9.8 or 10, something like that. This is the force pointing downward, but in order to have the equilibrium for the whole system, we should have also the force that is directed upward. Okay, the force should point upward, and to be in equilibrium, the force pointing upward caused by the magnetic field should be equal to the force caused by the weight of these two objects, the bird and the perch. Okay, once those forces are equal to each other according to the Newton's law, right? We could have equilibrium state. But what should the magnetic field line be directed in this scenario? Should it be pointed out of the paper or into the paper? What do you think? นะครับคิดว่าสนามแม่เหล็กนะครับควรมีทิศทางพุ่งเข้าไปในกระดานนี้นะครับหรือว่าพุ่งออกมาจากระนาบนี้ครับผม What do you think then? According to the formula F I L cross B, right? In order to get the force pointing upward, let's find from L to B, right? So L vector is this one. The vector L is in this direction. So in order to get F in this way, right, we want the force pointing upward to hold the weight of the perch and the bird, right? So we should have the magnetic field line pointing in this way, okay, which means the magnetic field line should directed into this page, okay, ก็คือสนามแม่เหล็กต้องพุ่งเข้าไปในแผ่นระนาบนี้นะครับเพื่อให้ได้แรง F ทิศชี้ขึ้นครับ okay, that's the first quantity we get F pointing. Okay, direction. The direction of the force, the magnetic field line, pointing okay ครับถ้าไม่มีใครแล้วก็จะขอปิดอันนี้นะครับ pointing into the plane. Okay, that's the first one, right, for physics. But another detail is the magnitude, right? F is directed into the plane because we could get the force pointing upward. Regarding the magnetic field, right, they want to find what is B in this scenario, right? And in this scenario, you can see that it's right angle, right? Here, right angle, 90 degree. So theta is 90 degree. From the general expression, F is absolute Q. Oh, no, sorry. I'll be right. Sine theta แบบ our phi is โอ้นั่นนะครับเกิด error ขึ้นนะครับ our phi is 90 so I is 4 ampere and L is 10 centimeter which is 0.1 meter and flux magnetic flux is what we want to know, right? Flux is B and sine theta sine of 90 degree will be number 1, right? This one is equal to 1. So we're gonna get F equal to 0.4b, right? But F here from the Newton's law, sigma F, right? Sigma F equals to 0 in equilibrium state. Or in scalar function นะผมไม่รู้ปากกาเกิดอะไรขึ้นครับ F equal to 0. So the force that is directed upward is going to be, let's say it's positive, F magnetic upward, and the weight of the bird is pointing downward, right? It's negative. Mass of bird plus mass of the perch times C, right? Equal to 0. Kg equal to 0. So it means F is equal to the mass of the bird, which is 1.6 plus the mass of the perch, which is 7 gram, but we need to convert it to SI system, right? Gram is 10 to -3, right? And G is, let's say, 9.8. So yeah, that's F. Okay, we would get the value of B by F divided by 0.4, but F is what we have here, which is 7.6. 7.6 times 9.8 times 10 to -3 divided by 0.4, right? And you can put this value into the calculator. Okay, okay, 7.6. One E3. Oh, negative. 0.1862. Okay, Tesla. The unit for the magnetic flux density นะครับปากกาผมไม่รู้เจ๊งหรืออะไรครับนะครับเกิดเส้นมาโดยที่ไม่ได้ตั้งใจครับ all right and that's it for this problem. Okay, 1862. ทำไมเขา210นะ4 ampere, right? 10 centimeter, 0.1, 1.6. Here 1.6 is 8.6 is not 7.6. My God, I'm stupid. .6. Okay, 2107. And that's the same value, right here, 2107. So now let's consider the next example. A wire carries a current of 22 ampere from west to east, okay, from the left to the right hand side. So the current should move in this way, right? From left to right, or west to east. And assume the magnetic field of the Earth at this location is horizontal and directed from south to north. What is that then? So we have south and north. Okay, the magnetic field vector is directed like that. And here is the vector L actually. Okay, vector L. Okay, we have vector L like this, the vector B like this. And it has a magnitude of 0.5 10 to negative 4 Tesla. Okay, this is the very little, the very light magnetic field caused by the Earth. By the magnitude and direction of the magnetic force on the 36 length of the connector. So it means we have the connector like this. The current moves from left to right, and the length here is 36, which is quite long. And the magnetic force or magnetic flux density, magnetic field line, is directed this way from south to north. B. Once you rotate your forefinger from the vector L to vector B, right, you can see that you turn your forefingers from this vector L to vector B, you will get this is vector B, this is vector L, the denoted force will be here, right? So it means that the force will go out of this page, okay, from this plane. The force will be directed to us, okay. And the next one is the magnitude, okay, the magnitude of the force, right? So F is I LB sine phi, right? When phi is 90 degree, I is the current, which is 22 ampere. 22 ampere times 36 meter, and B, which is 0.5 times 10 to negative 4. So you would have this is 11 and 36 is going to be 396 times 10 to negative 4. So it means 0.0396 Newton. Okay, it's not much. Okay, is that correct? 0.396. Yes, correct. The next one is calculate the gravitational force on the same length of the wire if it is made of copper and the density of the copper is 8.92 10 to 3 is heavier than water, and the cross-sectional area is 2.5 gravitational force, right? This is weight, or W, right? Actually, W is mg, right? But you know that rho, or density, is computed by the mass divided by the volume, right? And the shape of the conductor is like this. So it's cylinder. Okay, it's cylinder, and the volume of the cylinder is V of cylinder is A times L, right? The length, and as you know, A here, A is the circle, right? A is pi r square, so we're gonna get we will get เนี่ยครับไม่รู้เป็นอะไรนะครับปากกา pi r square and L, right? And you can substitute R, which is the cross-sectional area they have already provided. Okay, it's we don't have to insert the value of the radius at all. Oh my god. 2.5 times 10 to negative 6, right? Right, A is now 2.5 and L, right? The length of this copper is provided here 36 meter. That's 36. Okay. We would have 10 by 4. 10 by 4. So it's 90. It's 90 times 10 to negative 6 or 9 times 10 to negative 5. Right. It's cubic meter, right? And yeah, let's get back to this one. Mass will be the product between the product of density and the volume. We get already volume here. We know the density of the copper right here, and we need to compute the weight, right? So W will be empty, or in terms of density and volume, is going to be rho Vg, right? Rho is 2.5. No. 892 times 10 to 3, and V volume is 9 times 10 to negative 5, and the gravitational acceleration on that is 9.8. You can also use number 10 if you want. It's simpler. Now it's time to use the calculator. It's hard to compute it by hand, right? 8.92 E3 times 9 E minus 5 times 9.8. It's 786.744 Newton. Okay, that's the whole weight of gravitational force acting on this conductor. It's nothing with magnetic force. Actually, it's about the density of any matter. 786.744. Okay, now we arrive at the magnetic force between two conductors. Or let me check the time. I should leave you นะครับสำหรับคนที่มาใหม่นะครับคนที่เข้ามาใหม่ครับผมขออนุญาตแจ้งเดี๋ยวครับเช็คเวลาก่อนต้องปล่อยกี่โมงครับ Okay. At 10, right? I'm gonna leave you to get out of the classroom 10 โมงครับโอเคนะครับขอแจ้งครับคนที่เพิ่งเข้ามาใหม่นะครับภาษาไทยแล้วกันครับคือเนื่องจากสอนไม่ทันครับแล้วก็ข้อสอบครับออกถึงเรื่อง electric generator นะครับซึ่งท้ายๆนี่เลยนะไปเรื่อยๆครับ electric generator นะครับเนื่องจากสอนไม่ทันคือจริงๆแล้วข้อสอบออกในปีที่ยังไม่มีโควิดครับดังนั้นสอนห้องจริงมันจะเร็วนะครับพอสอนออนไลน์มันก็ช้าอย่างนี้นะครับก็ให้นักเรียนครับไปดูคลิปเพิ่มเติมนะครับจนถึงเรื่องของ electric generator นะครับตรงนี้นะครับใส่ไว้ใน Google Classroom ให้คุณนะครับ Students are required to watch one of the videos นะครับก็คืออย่างเช่น Lecture 18นะครับมี4ลิงก์คุณก็ดูอันนึงแล้วกันที่สัญญาณดีที่สุดภาพชัดสุดหรือถ้าคุณชอบดูของ604มันก็จะมี604 605นะครับคุณก็ดู604ก็ได้หรืออยากดู605ก็ได้ครับแล้วแต่ครับเหมือนกันครับดู Lecture 18นะครับของปีที่แล้วครับเดือนสิงหานะครับแล้วก็19 20 21 22 23 24 25 26นะครับนะประมาณ1 2 3 6 4 5 6 7 8 9 9อันนะครับเท่าไหร่8อันดิ8 9อันนะครับโอเคมาก็ให้ไปดูเลคเชอร์นะครับประมาณนี่แหละ2 คาบก็ประมาณ1.5 ชั่วโมงครับครั้งละ1.5 ชั่วโมงครับจนถึงหัวข้อสุดท้ายซึ่งเป็น electric generator นะครับลิงก์นี้ไม่มีเสียงครับให้ดูลิงก์นี้ครับโอเคผมดีนะครับที่อัดไว้ให้นะครับก็ปีนี้ก็อัดไว้อยู่ครับเผื่อรุ่นน้องคุณได้ใช้นะครับโอเคก็ประมาณนี้ครับขอแจ้งไว้ก่อนนะครับเสาร์อาทิตย์นี้นะครับไปดูนะครับคุณสอบวันที่8ใช่ไหมครับก็นั่นแหละครับถึงเลคเชอร์ตรงนี้นะครับ18อาจจะไม่ต้องดูแล้วนะครับเพราะว่าวันนี้กำลังสอนอยู่นะครับอาจจะเนื้อหาทับซ้อนคุณไม่ต้องดู18ก็ได้ดูเริ่มดู19ก็ได้ครับก็จะเหลือแค่8เลคเชอร์นะครับโอเคthat's what we need to have an agreement โอเคไม่คิดคะแนนเข้าเรียนนะครับคุณไม่ดูก็ไม่เป็นไรครับแต่ทำข้อสอบไม่ได้นะครับโอเคlet's continue the next topic which is the magnetic force between two conductors and as you know for a single conductor if you have magnetic field pointing this way you can curl your L right L to B you're gonna get the induced force pointing downward okay if there is another conductor the current flows in this way okay in the same direction it's gonna induce the magnetic field right around this long conductor Y by using the right hand you get the magnetic flux density vector like B here and yeah this magnetic field will pass through this conductor and it's gonna generate the induced force F pointing downward and of course the same way this conductor will also generate the induced magnetic field the magnetic field will pass through this one too and from L to B right you're gonna get induced force pointing upward okay so in short or in conclusion when the current flows in the same way for both conductor the force that take place on each conductor will be the attractive force okay the force that try to keep them to stay closer together okay to move to each other okay but yeah it's the same way from this book if you have the distance d from the conductor number 2 to number 1 and if this is the length okay we have distance d here the current flows in the same way and from the right hand rule the magnetic flux density will hit this point and going out of this right and from L to B right we cross the vector from L to B we're gonna get the the induced force pointing downward. And in the same way, because this current flow inside this conductor, that it will generate the induced magnetic field, and the magnetic field will, according to the right hand rule, right, it's going to hit this one and pointing in this way, right? So from L to B, right, to cross your vector L to vector B, you get the force pointing outward. So this is the attractive force again, right? Okay, but qualitatively, if we want to find the amount of the force, it's going to be F1, I1, LB2, right? Because the magnetic flux should be the magnetic field induced from another conductor, all right? And B2 could be computed by the BO Sawa, right, from the distance D. In mu0, it is mu0, I2, 2 pi D. If you substitute this one onto this expression, IL, mu0, I2 by 2 pi D, right, you're going to get this expression. Mu0, I1, I2, L divided by 2 pi D. And if you substitute this one, if you calculate it the same way for the force on the second conductor, you will get a you will get the same value of the force mu0 I1 I2 L divided by 2D. So yeah, the forces on both conductors will have the same magnitude. And if the current flow in the same way, you're gonna get the attractive force. If the current flow in the opposite way, you get the repulsive force. Okay, they try to go away from each other, but this one will try to attract them to stay closer together, right? Okay, you can see that F1 is equal to F2. If the current flow in the same direction, you get attractive force. But if the current flow in the opposite direction, the parallel conductors will repel each other. You get repulsive force. Okay, this is taken from the book in the bachelor degree. If you have a single conductor, you will get only induced magnetic field like this according to the right hand rule, right? It's gonna point like this, okay? And if you have the current flow in the same way, like this, okay, the magnetic flux will the magnetic field line will combine each other, right? Will make the superposition, and you will get attractive force. Okay, the force will try to keep these two conductors to stay closer. And if you have the current flowing in the opposite way, this one is up, this one is down, you will get the repulsive force. Okay, the force on the left hand side, on the left conductor, is gonna be here, okay, to the left. The force on the right conductor will be directed to the right. Okay, this is called repulsive force. Okay, let's consider an example about this. We have two wires, okay, because the topic is magnetic force between two conductors. We have two wires, each having a weight per unit length, weight, right? W per L is like this. Okay, W per L, 10 to -4 Newton per meter, are parallel with one directly above the other, so it's in the horizontal way. This one is up, another one is down, okay, in parallel. If we have the current flowing in the same magnitude, let's say it's I, but in the opposite direction. I'm sorry for that. Okay, if the current flow to the left for the lower one, the wires are 1 meter, 0.1 meter apart. This is distance D. And the sum of the magnetic force and the gravitational force on the upper wire is 0. So there will be induced force pointing upward. Okay, and there will be also the weight of this conductor, right? The upper conductor. Find the current in the Y's. Okay, find the currents in the Y. I don't know what formula. Okay, neglect the Earth's magnetic field. Okay, we don't pay attention to the Earth's magnetic field. Well, according to the formula here, I have mu 0 I 1 I 2 L 2 pi d, right? Okay, the force, because this is the current flowing in the opposite direction, so it's going to be repelling force, right? The force will be upward like this. Okay, and for this one, the force will be downward. Okay, yeah, according to the Newton's law, F sigma F remains 0, we're gonna have F equal to W, right? And W is mg, right? But we don't know. Okay, let's consider the left hand side. It's mu 0 I1 I2 is the same. Okay, this is I1 equal to I2, which is the same amount I. So I would be I square mu 0 I Li, right? Li divided by pi d squared, pi 2 pi d, right? 2 pi d. And it's going to be W, right? But what they want to know is the current, which is this one, right? But this one is I square. We get I square equal to W per L, right? The first factor. And 2 pi d divided by mu 0, right? And let's compute it. Okay, I square will be W per L is what they provide here, 10 to negative 4. Okay, 10 to negative 4. And 2 is 2, pi is pi, d is the distance, which is 0.1. And in the lower part is mu 0 for the constant, right? The permeability in vacuum is 4 pi times 10 to negative 7. You can cancel this one, and 2 right here. Okay, now you get 10 to negative 5 times 10 1 by 2, 10 to negative 5, and 10 to 7, right? It's 100 by 2, or it's actually 50, right? But it's not I, it's I squared. So I will be the square root of 50, which is 5 square root 2, okay, or 5 times 1.414. It's 7.07, right? Ampere. I think so. Yeah, 7.07 ampere. Okay. Now let's consider the next example. ถ้าใครมีปัญหามีคำถามนะครับโปรดถามได้เลยนะครับว่าอาจารย์ไปเร็วไปหรืออะไรอย่างนี้นะครับ Let's consider the next example. Two thread parallel superconducting cable. What does that mean? Superconductor means R is 0. Okay, the resistance of that conductor is 0. Superconducting cables. And 4.5 meter apart, so D is 4.5. Carry equal currents of very large, 15,000 in the opposite direction to find the magnitude and direction of the force per unit length. exerted on one conductor on the other, should be concerned about the mechanical strength of this wire. Okay, let's consider the first question first. Magnitude and direction. Let's draw something. Well, super conductor like this. The current flows in the opposite direction, left to right, right to left, and I is 15,000 ampere, 4.5 D. Okay, direction, but of course, okay, once you have the current flowing in the opposite direction, it means the force will be repulsive. Okay, it's gonna move this one out of the pair. The force is gonna move this one out of the pair too. Okay, repulsive force. That's the direction. Okay, and magnitude, of course, F could be computed from mu0 because I will be the same, right? Okay, I, this one is also I, right? Mu0 I1 I, right? But I2 is also I times L, right? Divided by 2 pi d, right? But what they want to know is force per unit length. What is that? Force per unit length. So yes, we can get F by L, right? F by L expression will be mu0, right? Mu0 I square divided by 2 pi d, right? So let's start to substitute. Mu0 is 4 pi times 10 to negative 7 I square. I is 15,000, 15 times 10 to 3 square divided by 2 pi, and d is the distance, it's only 4.5, so it can cancel. Number 2 here, and you get all right, here is number 2, and 225 times 10 to negative 7, 10 to 6, right, divided by 4.5. All right, we could do we could not do anything more. Okay, it's above, you have 450 and 10 to negative 1, and you have 4.5 here, right? It's gonna be 100 and 10 to negative 1, right? It's actually equal to 10. F per L is Newton per meter, right? 10 Newton per meter. Oh, 1000. 4 pi 10 to negative 7. 15,000. Yes. 2 pi d. Millimeter. My God, I'm stupid. This is 40.5 millimeter. I'm stupid. Okay, so this one will be also 10 to negative 3. times 10 to negative 3. So once you move 2b upper, it's going to be 10 to 3, right? So it's going to be 100 here, and that's why you 1000. Okay, 1000 Newton per meter. What is that then? Let's consider it in reality. If you have a long straight conductor and for 1 meter you leave something like 90 kilogram onto 1 meter of the conductor. What do you think, whether it can sustain or not? นะครับถ้าคุณมีเส้นลวดนะครับสัก1 เมตรยาว1 เมตรมีน้ำหนักไปกดทับ 1,000 นิวตันนะครับหรือว่าน้ำหนักทางกิโลก็จะเป็นง่ายๆก็คือ100 กิโลคุณคิดว่าเส้นลวดมันจะรับได้ไหมเส้นลวด1 เมตรครับแล้วก็เอาคนหนัก100 กิโลไปนั่งตรงเส้นลวดครับแล้วขึง2 ปลายทั้ง2 ด้านของเส้นลวดมันจะทนได้ไหมก็คงทนไม่ได้ครับเพราะว่า strength มันไม่เพียงพอก็จะขาดครับก็คือ this way the mechanical strength of this wire might not be sufficient. Okay, we could not build up this system because the force is too much so that the wire can sustain with that. Okay, let's move to the next one, which is talk on a current loop and solenoid. Okay, we have the magnetic force act on side like this, right? If you have the loop of the conductor, whether it's square, circle, or any kind of shape of the conductor, if the magnetic flux is directed to the right, like this. Okay, if this side has the length of A and this side has the length of B, we insert the current somehow so that the current will rotate like this. And of course, in this way, the angle is 180, sine of 180 is 0. Sine of 180 degree is 0, so there is no force at all acting on this environment. And in this environment, sine of 0 degree will be also 0. So there is no force acting on this component. This component has also no force. But this one, the angle is 90, right? Sine 90 degree is equal to 1. So there is force acting on this bar, this component. And also this one, the angle is 90 degree, right? There is force acting on this vertical line, vertical conductor. But this one from L to B, we cross the vector from L to B, right? We're gonna get the force pointing up. And this one, L to B, right? We're gonna get the force pointing down. Okay, it means this conductor loop will rotate because there is moment. If this one is the middle, it's gonna rotate around the center of this one because this is the upward force, downward force. This one is pushing, this one is pulling, so the whole conductor here will rotate. จินตนาการทันไหมครับอันนี้มีแรงดึงขึ้นนะครับอันนี้มีแรงดึงลงเส้นลวดนี้ก็จะหมุนแล้วครับทีนี้หมุนนะครับเป็นที่มาที่ไปว่ามอเตอร์ก่อให้เกิดทอร์กนะครับนี่คือหลักการของมอเตอร์นะครับโอเคif you look at it if you look at this figure from the side view สมมุติเราเอาตาไปมองขึ้นไปด้านนี้นะครับมองด้านข้าง you're gonna see the force on the right hand is pointing downward. The force on the left hand is pointing upward. So it's gonna rotate. Okay, and the moment which is known also to us as torque. Okay, torque is moment. Moment is force multiplied distance. Okay, multiplied by distance. So this one will be moment here. Moment on the right hand side will be F2 times A divided by 2. Okay, moment on the left hand side will be moment number 1, which is force number 1 times the distance. Okay, because the whole length here is A, right? The whole length is A. You have divided into 2 parts. Each is with A by 2, so it's gonna be A by 2 also on the left. Okay, the moment on the left hand side will be similar to the moment on the right hand side. And if it's rotated a little bit by angle theta, okay, now this is the normal vector, right? This is the normal vector, the vector that is perpendicular to the plane of the conductor. If the normal vector is at angle theta to magnetic flux vector B, F will be different, okay, because the normal vector is not 90 degrees at angle theta. So in this one, we're gonna use F2 as ILB sine theta, right? Or sine phi. Okay, this F will be also ILB sine theta, right? Once you combine the torque, right? Torque on both sides. Okay, the torque will be the summation of this one, right? Which is F1, F2 times A plus 2, right? But if F is the same, okay, if F1 and F2 is the same, F1 and F2 are the same, so we just use this value and times the distance A by 2, right? Please note that length here is B. Okay, the length is B. This is B, small b, right? So if you combine all these moments, F1 A by 2 plus F2 A by 2, because F1 is equal to F2, which is IBB sine theta. Okay, we substitute F1, F2 into this expression. We're going to get M equal to F times A, and F is IBA B sine theta. And BA is, what is that? BA is the area actually. Okay, if you multiply B and A, it's the area of this square. Area is B and A. Okay, so you get area for this one. So this one is IAB sine theta. All right. Yeah. Once you combine the moments, okay, in terms of torque, you're gonna get something like this. Each one is IBB, right? And once you combine, it's gonna be, you can say E bar or B sine theta. Okay, the way to memorize this formula, B sine theta or E bar or I don't know RB or whatever what you can, whatever technique you can use to memorize this formula. But the important thing is I times A is known as magnetic moment of the loop. Okay, this is the characteristic of the conductor. Okay, the product between current and the area. It's denoted by the unit of it has the unit of ampere times square meter, because ampere is the unit of the current, the square meter is the unit of the area, right? So that's why we have ampere meter square meter. Okay, A is the product between A and B. That's the rectangle area of the conductor loop. This analysis is valid for any shape of conductor, not only the square conductor. If you have the circle, oval, ellipse, whatever shape of the conductor, you will always get this one, BR sine phi sine theta. But in order to derive the one for ellipse or circle, okay, it's going to be more complicated. The simplest way is to consider the rectangle conductor loop like this. Well, torque max, okay, the maximum value of this one, and as you know, the psi function is like this, right? Right. So this is phi is 0 and its maximum at theta is equal to 90 degrees. So the psi function will be maximum at theta equal to 90. So once the sine 90 is substituted, when 90 degrees is substituted, it's going to be sine 90, which is number one. So torque max is BR, okay, BIA. Magnetic flux density, current, and the area of that conductor loop. Okay, now let's take a look at a more complicated figure. In this one, we have the conductor loop like rectangle. The length here is A, the length here is B. Okay, and magnetic flux is pointing upward. Okay, you can see the blue light here, magnetic flux density, magnetic field light is pointing upward. And they use an alternative variable. They use phi, okay, instead of theta. The first right here, after you cross your your fingers from the right hand rule, right? L, vector L is like this, and B, right? L to B is gonna bring you to the force pointing to the positive x-axis. And the current flow in this way, right? The vector L is gonna be this way, L to B, right? You cross your forefinger from L to B, you will get the force in this direction. Okay, and the force here will be only in the opposite direction, but the magnitude will be the same. Okay, the forces on both sides we have share the same magnitude. Yeah, it will rotate like this, but if you take a look at this, you can have the induced force also, but L to B, right, is gonna be the force pointing in this direction. L to B, right, L to B, you're gonna get the force pointing in this direction. But they will not move the force, they will not move the conductor loop, because the forces here share the same magnitude, but only in the opposite direction. So they will cancel each other. Everything will remain in equilibrium along this axis. But this one is not equilibrium. There will be moment, so the conductor will rotate like this. Okay. Just in this setup, you can see that we will end up with the BR sine phi, okay, instead of theta. They change only theta and phi. Okay, this is taken from a different book. Okay. This torque will be maximum when the normal vector of the plane of the conductor loop is at 90 degrees to the magnetic field vector. Okay, if the magnetic field vector is pointing up, normal vector of this conductor is pointed to the left or to the right like this. So this will be the maximum force that happens to the conductor loop because the angle is 90 degrees. Yes, the maximum will be here again. Okay, and let's consider when the normal vector is in the same way, in the same direction to the magnetic field lines. You can see that the angle between normal vector and the magnetic field line will be 0 because they point in the same direction. When you substitute psi to be 0, psi of angle 0, yes, of course, at this state, there will be no force at all, okay, because they will cancel each other. There will be no moment. I'm sorry, but there is no torque at all. There are still forces, but they cancel each other, okay, in this direction. And that's the minimum of the torque. Okay, minimum value of the torque will be 0. It will be 0. And if you have a large number of rounds of the conductor, okay, you turn it with several rounds. Okay, number of turns is very much, it's like n turns or something like that. You get n amount, okay, n times this thing. Okay, n times the torque here, n will appear here. The formula now will become BIAN. Okay, n, the capital N is the number of turns นะครับจำนวนขดที่คุณจะขดอันนี้เป็นขดเดียวก็เป็นเลข1ครับโอเคถ้ามีหลายขดอย่างนี้ก็จะเป็น n ใหญ่ครับonce we arrange it in a solenoid way, right, we have many loops, and if the number of loop is capital N, okay, the torque will be the superposition. Okay, they will add each other. We're gonna have Bian, okay, or you can memorize it that I-bar or Bar-in or whatever you want. Okay, I would prefer Bian. Okay, BIAN, psi phi, and mu n here is the magnetic moment, which is the behavior of the conductor. Okay, Bian, IAN. Okay, without B. Okay, now let's consider this example. We have circular coil of the Y. Okay, this is circle. Okay, with average radius 0.05 with 30 turns, lies in the horizontal plane. It carries the current of 5 ampere in a counterclockwise sense. So if you have conductor like this, the currents flow in this way counterclockwise, okay, and return to this one. Okay, this is the top view, when view above, right? The coil is in uniform magnetic field direct toward the right. So magnetic field is directed in this way. This is magnetic field B. With magnitude 1.2, find the magnetic moment and the torque. Okay, you could find the magnetic moment from mu n, right, is IAN. So current is 5. The area is pi r square, right? R square 0.05. square, that's A. N is the number of turns. They have like 30 turns, right? So this one is, this is 25. Okay, 0.25, and this is also 5. Okay, it's equal to 0.25 times 150 of pi. That's the magnetic moment. 2.5, right? 1 by 4, 1 by 4, right? 1 by 4. It's 3 7.5 pi. Okay, we can have it หมดเวลาแล้วครับแต่เดี๋ยวผมขอจบข้อนี้ก่อนครับ you can have the exact value from this one. I don't know what is that. 37.5 pi. 37.5 pi 117.8 approximately 117.8. The unit is ampere square meter, right? And for the torque, we just have the torque is BN psi, right? BN psi phi. This one we have the normal pointing upward, and the phi is 90 degree, right? So B is 1.2 times this thing, right? Which is the 37.5 pi, and here is sine of 90, which is actually number 1. Okay, you multiply 1.2 and 35. เดี๋ยวครับเพิ่มหน้ามาเลยนะจะได้ง่ายๆนะtimes 1.2 141.37 141.37 Newton meter, right? That's the moment, force, and distance. Let's see whether it's correct or not. 0. Oh, without n, okay, that's the, and with n we're gonna have 1.17. Huh? 0. Oh, this one, my god, stupid. 0.0025, my god. And that's the 0.375. Okay, and we're gonna get 1178. Okay. Yes, and this one is not 37, it's 0.37. Okay, we would get 1.41. 1.41, okay, approximately. Newton meter. 1.41. The torque. So what? Here the sketch of that problem. So how it rotates then? Vector L is like this, right? L. Vector B is like this. So it's gonna be up, right? The force is gonna be up. And on this, at this right, the force is gonna be down. So if you look at the side view, it's gonna rotate in the counterclockwise direction. Okay, this connector will rotate. On the left side will go down, on the right side is going up, so it is counterclockwise direction. Okay, and that's it for the lecture of ตามทันเนื้อหานะครับเพื่อใช้ในการสอบครับ See you on after the midterm exam. Okay, if you have any question, just let me know. Please don't forget to write down your name. Oh, in this one, okay, in the Zoom chat box. Okay, please don't forget to write down your name. นะครับบ๊ายบายครับสวัสดีครับ So this is the M604 right the last oneใช่ครับtoo many video คือคันที่นั้นนะครับก็คือว่าไม่ได้ดูทั้งหมดนะครับให้ดูเฉพาะ1อันเท่านั้นนะครับคุณเลือกเอาที่มันชัดนะครับผมพยายามมีหลายอันนะครับให้คุณเลือกเอาที่คุณภาพภาพและเสียงดีที่สุดนะครับสำหรับคันที่นั้นนะครับมีให้เลือกเยอะนะครับผมอัดไว้ครับอันนี้ก็เหมือนกันนะครับปีนี้ก็อัดไว้เยอะผมไม่รู้ว่าบางทีบางช่องนะครับมันก็เสียงภาพหายเกิดปัญหาอย่างเงี้ยครับก็เลยต้องอัดหลายๆทางครับเพื่อว่าป้องกันปัญหานะครับyes 8 lecture ครับใช่ครับมี8 lecture เท่านั้นครับก็จริงๆวันนี้เรียนไปบ้างแล้วนะครับประมาณ8 ชั่วโมงใช่ครับวันนี้เรียนไปบ้างแล้วคุณอาจจะไม่ต้องเริ่มอันแรกนะครับมันอาจจะลดลงมาเหลือ6เหลือ7 lecture เท่านั้นครับเวอร์ชั่นของปีแรกครับที่ไม่ได้เป็นโควิดซึ่งอันนั้นอะไปได้เยอะครับโอเคไหมอย่างวันนี้เรียนไปแล้ว18อาจจะไม่ต้องดูแล้วครับ4อันนี้คุณไม่ต้องดูทั้งหมดนะครับคุณดูแค่อันนึงนะครับผมไม่รู้ว่าอันไหนคุณภาพดีสุดผมหามาได้4อันนะครับคุณก็เปิดดูแล้วกันครับคุณชอบภาพจากซูมคุณชอบภาพจากอะไรนะครับโอเคมาเปิดดูนะครับมีพิมพ์มานะครับ so it's around 8 hours plus ประมาณนั้นครับ8 ชั่วโมงกว่าประมาณนั้นนะครับจนถึงสุดท้ายครับจนถึงสุดท้ายซึ่งเรื่อง electric generator ผมว่าเราน่าจะเซฟไปได้สัก1-2 อัน1 หรือ 2 อันแล้วนะครับก็สตาร์ทที่20ก็ได้ครับถ้าคุณรู้สึกว่า20เนื้อหามันขาดหายก็ไปเริ่มที่19นะครับโอเคไหมแต่วันนี้น่าจะไป18ให้คุณนะครับพอได้นะครับพอเข้าใจเนาะพนัชชัยนี่604เนาะพนัชชัยครับผมไม่รู้ว่าเขาจะให้ ขยับข้อสอบได้หรือเปล่านะครับเพราะว่ามันอาจจะอยู่ในขั้นตอนการแบบว่าโลเนียลแล้วอะไรอย่างเงี้ยครับผมถ้ามันโลเนียลแล้วมันก็แก้ไม่ได้ครับเดี๋ยวนะครับขอเก็บชื่ออัทรชัยผมไปดูแล้วอ้าวโอ้โหเวลาเราไม่พอนะครับก็เลยส่งลิงก์ให้คุณเพื่อไปนั่งดูนะครับโอเค alright 5 คนโอเค This is M604 for today, right? 01.07 2022. Okay. โอเคครับ605นะครับ ธนากรหมายเลข21นะครับ พิมพ์มานะครับ ที่ YouTube นะครับ เขาดูที่ YouTube นะครับ ก็แล้วแต่ครับ Oh, what happened? There was an internet connection problem. Okay, reconnected. Ten 20, right? That's the same time for M605. Okay, I think it's time now for the section of M605. All right. We have to stop at 11:40, right? 11:40. It's time for us. Okay. The first person should be okay. The first one is Peter Don of M605. All right. Good morning, everyone. Welcome you to SCI33205. I don't know whether we still have someone to get in to the crew the Zoom classroom. This is for. Oh no! My God! All right. We arrive at the. ALB sine theta, right? We have already discussed something about it. Okay, we arrive at this figure, if I can remember properly. Yes, the drift velocity, right? The chart, we have chart flowing through the conductor lines like this นะครับก็ขออนุญาตแจ้งตรงนี้ก่อนแล้วกันนะครับสำหรับคนที่เพิ่งมาใหม่นะครับเนื่องจากข้อสอบนั้นผมส่งเวอร์ชั่นของปีที่เป็นเรียนตอนยังไม่มีโควิดครับโควิดยังไม่ระบาดหนักครับตอนนั้นก็ห้องจริงกันแล้วมันไปได้เร็วนะครับปรากฏว่าผมได้ไปส่งข้อสอบเวอร์ชันนั้นนะครับแล้วก็มันจบที่electric generator นะครับซึ่งเลยอันนี้ไปพอสมควรนะก็ดังนั้นเพื่อให้ตามไม่ทันนะครับก็ขอรบกวนนักเรียนนะครับให้เข้าไปที่ลิงก์นี้นะที่ Google Classroom ซึ่งมันจะมี list ครับ Students are required to watch one of the videos for each lecture listed below in order to keep up with the midterm exam นะครับมันจบ the last topic that the midterm exam will cover is electric generator. So electric generator will be somewhere here in the 26th lecture from the last year video. So but you may skip this one, okay? The video here would be taught by me today in this lecture, and you may start from 19, 20, 21st, 22nd, 23rd, 24th, 25th, and the last one. Okay. There are so many links. Okay, you just choose only one that you feel it has great video quality, great sound quality. There is no delay because last year is the first year that I have several apparatus devices. Okay, and I may not use it properly. Sometimes the video record doesn't have the sound at all. For example, this link. Okay, and last year I didn't have there was no strong internet fiber and it was taught in online. Several colleagues may use the internet bandwidth and the video stream may get stuck somehow, so you may get trouble somehow. But this year I use my own fiber optic internet, so it's very smooth, right? As you can see here. Okay, choose only one link that you feel it's very comfortable for you to watch, and don't watch the whole thing. Maybe in some videos they provide both M604 and M605 sections. Take only one section that belongs to you, or you want to watch the M604 section, it's up to you, but they will be the same. alright นะครับวิศพลที่Streamlab นะครับ okay yes you can also type your name in the YouTube channel it's no problem นะครับรุ่นพี่คุณไม่ค่อยได้เข้ามาที่ Zoom นะครับเข้ามาที่ Zoom แค่คนเดียวนะปีที่แล้วนะครับหลังๆมานอกนั้นไปที่ YouTube กันหมดนะครับ okay yes and these are the video records that try to give it to you so that you can reach the topic of electric generator. That's the last topic in the second part of the midterm exam. Alright นะครับแจ้งไว้ก่อนนะครับบอกเพื่อนด้วยนะครับถ้าเพื่อนมาทีหลังครับอาคีราด้วยนะครับผมต้องพูดหลายรอบเสียเวลาครับบอกอาคีระด้วยนะครับว่าให้ดูวิดีโอนะครับโอเคอาคีระเข้ามาใหม่นะครับให้ดูวิดีโอนะครับตรงพวกนี้นะครับเพราะว่าเราจะสอบกันถึงเรื่อง electric generator นะครับก็คือเครื่องกำเนิดไฟฟ้านะครับตะกี้604จบที่ talk beyond side นะครับก็โอเคในระดับหนึ่งน่าจะ18-19นะครับโอเคมาก็ไม่ต้องดู18-19ของ604ของเราไม่รู้เท่าไหร่นะครับก็ให้คุณไปเลือกดูลิงก์1อันนะครับอันไหนก็ได้นะครับที่คุณรู้สึกว่าคุณภาพวิดีโอดีไม่กระตุกเสียงชัดเจนนะครับก็เลือกดูเอานะครับแค่อันเดียวนะดูเสียเวลาเยอะนะครับโอเคถ้าดูหลายอันนะครับก็ไล่ดูมาเรื่อยๆนะครับจนถึงอันที่26ครับก็คือเรื่องของ electric generator นะครับโอเคมาก็ประมาณนั้นนะครับthen anyone else นะครับถ้าผมปิดไปนะครับผมไม่ได้รับคุณเข้าชมก็ดูที่ YouTube แล้วกันครับหรือไม่ก็ให้เพื่อนแจ้งผมว่าอาจารย์ครับรับเพื่อนเข้า YouTube หน่อยครับเพราะว่าเวลาสอนแล้วผมก็จะปิดหน้านี้นะเพื่อใช้หน้านี้เต็มๆ Okay we start from the chart that moves inside the conductor right and if this area has the magnetic field line pointing what is the X side here the magnetic field lines is directed into this page, right? We see only the rear part of the arrow. And if there is the cross-sectional area of the conductor as the circle, if this cross-sectional area denoted by A is known, okay, we could find the induced force, right? In physics, we have two things, right? The direction and the magnitude, right? You start from FQVB, right? V cross B, this is V, and you have B pointing into this page. And then you get F, which is the induced force pointing upward. Okay, and if this is the length of the conductor that you want to consider, right? Yeah, that's FQVB, all right? Regarding the okay, you can rotate your four fingers from vector V to vector B, you get the force pointing upward. Regarding the magnitude, which is another one in physics, we have the formula QVB sine theta, right? But in this orientation, the angle between the vector V and vector B is 90 degrees, so we get theta of 90 degrees, and that side 90 degrees is number one, right? So finally we have F as absolute QVB. And if we have several particles, not only this one, we have like a capital N moving particles. Okay, when N is the index of the charged particle, the force here will be separated. Okay, the force will take place for each particle. In that sense, okay, for the N moving charged particle, we're going to have F with subscript N, okay, and the charge of the N particle, the drift velocity, because it is possible that each charge may move with a different speed or low or velocity, and we would prefer to use the drift velocity, which is the average value of the velocity or the speed, okay, VD. And once we substitute, once we know drift velocity, we know the magnetic flux density, we leave it into this computation. And if we have capital N particles at a constant speed Vd, okay, all of them move with the same average value Vd, we would have, of course, from material 4, you know that velocity or speed is the distance per time, right? If we observe the movement of this charge from this point to this point, and it lasts delta t time, okay, whether it's 1 second, 2 seconds, or 3 seconds, delta t is the observation time. So the speed will be distance, which is distance here, okay, the length of the conductor that we want to observe, divided by the time that we spend, okay, to observe that movement, okay. And นะครับไม่มีใครผมขออนุญาตปิดอันนี้นะครับ and here we have long straight copper wire, and if in this area we there is a magnetic field, magnetic flux density like this, okay, the magnetic field lines are pointing into this page, the plane of these lecture notes. And if both ends of the connector are fixed like this, okay, we fix it by using any method. So this one will be flexible, right? This part of the connector will be flexible, and if there is no current, okay, we don't let the current flow at all through this connector line. I is 0. Yes, of course, there is nothing happening, right? But if you let the current flow upward like this, okay, flow from the bottom to the top, of course, its original position is going to be like this, okay. But the vector v, drift velocity, is going to point upward, and you rotate your 4 fingers from v, vector v, to the magnetic flux density vector b, you would get the force that points to the left hand side. So the force here is going to bend, okay, try to force this conductor a little bit bend to the left. And if you have the drift velocity of the shaft moving downward, this is the velocity velocity vector pointing downward. You rotate your 4 finger from this vector to the vector pointing into this page. You're going to get the induced force pointing to the right. And with this effect, the force try to bend all conductor on this part, okay. There is force here. There is no force in this area because there is no magnetic flux. There is no force in this area. There is only force in this area, okay, pointing to the right because of the magnetic flux, okay. So with this continuous force, they're gonna bend this conductor to the right, okay. In conclusion, if there is no current, the conductor will be in the long straight way. But if there is current, whether in the upward direction, downward direction, the conductor will be a little bit bent like this, okay. Now let's get back to how we determine the force, okay, due to several particles, okay, moving inside the conductor. If the capital Q is the total amount of the charge, okay, we have n particles, or like n electron, okay, million electron, n is 1 million, okay, capital N is 1 million, okay. The total charge, the total amount of charge will be the summation of all charge, okay, the summation of all charge, and we don't care whether it's negative or positive, so it's absolute value, okay. And from the theory of the current, right? Current is the charge movement per time, right? This is the basic ratio, and this is the basic summation that we need to keep in mind. The next one is we consider the total continuous force in this area, right? If we have capital N particle, of course the force is going to be the summation of all N forces. Okay, and yes, Fn will be Qn VdB. Okay, according to the previous formula, and yeah, this is the force caused by the N particle. But the summation depends only N here. Okay, there is no N dependence on Vd and B. The summation here is the big Q, the capital Q, and velocity here is L by delta T, right? L by delta T is distance by time, right? That's the drift velocity. And if we express the capital Q here, right? And if we move the denominator here, delta T by Q, right? It's going to be current. Or you multiply delta T here, it's I delta T, right? So you cancel this one, it's going to be ILB. Okay. This result, ILB, is valid when your conductor is situated at 90 degrees from the magnetic flux density, magnetic flux vector. If it is oriented a little bit with angle theta like this, okay, it's not situated at 90 degrees with respect to the magnetic field anymore. If it lies in a certain angle theta, which is not 90 degrees, we have to project. Okay, we have to project the magnetic field to the perpendicular component like this and the parallel one. The parallel one has no effect to the force at all, because if you cross your vector this way from vector L, okay, to this B, the angle is 0. There is nothing happening, right? But this one is useful, right? Because it's 90 degrees with respect to the velocity vector of the charged particle. So we project the original component, which is made at angle phi. So this one is going to be B psi. Okay, B cosine has no impact to us. Okay, has no effect to the force. Now we project the magnetic flux to the perpendicular component, which is B psi phi. The expression in 35 actually comes from the cross product, which is L cross B here, right? F is I L cross B, is not Q V cross B anymore. Okay, L is the vector along the length L of the conductor. Okay, it's the same direction as the current movement. Okay, so how we can determine L to B, right? This is vector L, this is vector B. You rotate your forefinger here. Your thumb direction will give you the induced force direction here, okay, pointing upward. Okay, and in the next scenario, your vector L is like this, right? You cannot rotate to this one because the angle is greater than 180 degrees. Okay, you need to rotate in this way. Okay, when the angle is less than 180 degrees. Okay, and once you use your right hand, okay, you rotate your four fingers like this. Your thumb direction will give you the induced force downward like this. Okay. If they lay down the conductor, they flip the conductor to the opposite way. The current is flowing out of the original location. L to B like this, right? You cross your vector from L to B. Your thumb direction will give you the direction of the induced force pointing upward. And what is the application of FILB, or what we are studying here? The application is a speaker you can see the speaker, right? The electronic device that can increase your voice, increase the sound of your voice or music or so on. Okay, if this one is very big, you're gonna get very loud music or voice of somebody. Okay, the speaker has two components. Okay, this one is paper cone, and this is the paper also that that can move freely, okay, easily through this one. We have the north pole in the middle. We have two south poles at the end, and of course the magnetic field line starts from the magnetic north pole to the magnetic south pole. Okay, the magnetic field line will directed upward like this. Magnetic field line will directed downward like this. And if we have the solenoid or several rounds of the connector around this one, okay, the connector here is attached to the paper cylinder here. Okay, if we let the current flow like this, okay, the current goes into the page, okay, at the lower part, and the current is going out of the plane at the upper part. All right, and we will get FILB, right? L is going to be the length vector of at the location, so it's going to be point out of the page, and you rotate your forefinger from L to B, you're going to get a force to the left side, okay, in the upper part. And here the lower part, the current is going into the page, and you rotate your forefingers from direction here to the magnetic flux density vector. Here you get the force also to the left, okay, in the left direction. Okay, the total force will be the force to the left, okay, but if you reverse the current, the force is going to be point directed to the right. Okay, yes, you can change the frequency of the current according to your music, according to your sounds, by using the amplifier. Okay, amplifier is the device that insert the current, okay, the device that inserts the current through the solenoid, so that the cone here will vibrate according to the frequency that you want to transfer. Once the paper cone moves, okay, they're gonna compress the air, and the air with the compressed will be the sound wave to our ears. Okay, we can hear the music and so on from the compression of this paper cone to the air. Okay, the air in this area. Okay. Once you know the application, let's talk about the first example regarding the FILB formula. Okay, you know that the world lightest animal is the world lightest bird is the hummingbird, right? Hummingbird is even smaller than some insects, some butterfly. Okay, but the hummingbird is different from sorry insect, right? Because they have their own bone, right? Okay, the hummingbird is the smallest bird on Earth. Its mass is 1.6 gram. Okay, it has its own mass. And we want to build up a long straight bar, or it's known as perch, okay, that can support the hummingbird, okay, to stand up. When we say it can support, it means that all of these particles, of these two things, the bird, the conductor Y, will stay in equilibrium, right? So in equilibrium state, it means that summation of F remains zero, right? According to the Newton's law. It means that the force that try to lift the bird up and the force that the force of the gravitational force caused by the bird and the perch will be in downward direction, right? There would be these two forces would be the same in magnitude, right? Would be equal to each other in magnitude. So the question, what is that? The perch is 10 centimeter long. It has a mass of 7 grams, and the current that flows in through this conductor is 4 ampere. Okay, what are the direction and magnitude of the magnetic field? So we need to find what direction should the magnetic field directed, and what direction, what is the value of the magnetic flux density, so that all this stuff will stay in equilibrium state. You mean the lifting force and the downward force would be the same. Okay. In order to determine the direction, okay, let's see. The current flow in this way is vector L. In order to get the lifting force, we need the direction of the magnetic flux density, right? L2B, right? So this is vector L. Vector B should be in this way, so that we can get the lifting force like this. Okay, this is the three-dimensional drawing of this one. L to B, right? We get the time direction pointing upward, and that's correspond to vector F here. Okay, so the magnetic field should okay, this is the answer for the direction. Okay, the magnetic flux should pointed or directed into this plane. And what about the magnitude? What is B then? Okay, you know that an object has the lifting force and W weight, right? From the Newton's law, if sigma F is equal to 0, we're gonna get F equal to W. But F from the magnetic is F I L B, and in this sense, if the magnetic field is directed into this space, the angle is 90 degrees, so we're gonna have sine of 90 degrees, so it's number 1 here, right? Let's substitute I and LB. I is 4, L is 0.1, B magnetic flux density. They want to know B, right? But this is B, right? So it's 0.4 B. From the Newton, we would have the mass mg, right? But this mass should be the mass caused by the bird and the perch. So F will be mass of the bird plus the mass of the perch times G, which is 9.8. Okay, let's substitute that. Mass of the bird is 1.6 gram, plus the mass of the perch is 7 gram, but we need to convert it to the SI system kilogram, right? It's going to be 10 to negative 3, and G is 9.8, right? Here we have 8.6 times 9.8 times 10 to negative 3. And according to this relation, B will be F by 0.4. B is F divided by 0.4. So F is this amount, 8.6. 8.6 and 9.8 times 10 to negative 3 divided by 0.4. Okay, let's compute this. (8.6) times 9.8 e minus 3 divided by 0.4. And we get 0.2107. It's equal to 0.2107 Tesla. Is that correct? Yeah, it's correct. Okay. Let's move to the next example. Okay. A wire carries a current of 22 amperes from west to east. Okay, west to east means left to right, right? West to east. And assume that the magnetic field at this location caused by the Earth is horizontal and directed from the south to the north. So this is vector L, and here is vector B from the south to the north. It has the magnitude of 0.5, 10 to negative 4. Find the magnitude and direction of the magnetic force on 36 meter length of Y. So the conductor lies in this way, right? And is 36 meter like this. Okay, you start from B. Oh, sorry. You start from L to B, right? From L to B. The force is the force that you get. Let's draw it in 3 dimensions. This is vector B. The force you get from the induction will be like this. Okay. It's gonna point out of this page, directed to us. Yeah, the force. Okay, that's the direction. But for the magnitude, we're gonna need to go into the detail. Magnitude of the force, right? F is I L B psi theta or psi phi, up to you. The vector here, the angle here is 90 degrees. So psi 90, right? So this one I 22 ampere and L the length is 36. B is 0.5 times 10 to negative 4 and psi of 90 degrees. Well, it's number 1, right? This one. So we're gonna get 11, 3, 9, 6 times 10 to negative 4. So it means it's equal to 0.0396 Newton, right? Correct or not? Is that correct? Okay, correct. All right, 0.9396. Let's consider the next thing, the next question. Calculate the gravitational force on the same length of Y if it is made of copper with density 8.92 10 to 3 kilogram per cubic meter and cross-sectional area is 2.5. 10 to negative 6. All right. So the gravitational force, right, which is W, right, mg. Okay. Of course, G we know is 9.8 meter per second square. And the mass of conductor, right? The mass is, oh, I don't know. Rho is m by v, right? The mass divided by the volume. If you want to find the mass will be the product between rho density and the volume. So we get rho and v, g, right? And but v volume of this one will be the product of cross-sectional area times the length, right? So simply speaking, rho volume will be A times L, right? Because you have the length here as L, the length. So we substitute AL to this expression. It's going to be rho ALT. Now let's compute everything. Rho is 892 times 10 to 3. That's rho. And A cross-sectional area is 2.5. 10 to negative 6. And L is the length. They consider the length of 36 meter. Okay. So we get 36 right here. And then 9.8, right, meter per second square. Okay. I don't want to use the hand. We will use the calculator. 8.92 E3 times 2.5. 2.5 E minus 6 times 36 prime 9 times 9.8. So we get 786 approximately. Or exactly, I think. There's no pi, right? Okay, exact. 7.86744. That's Newton. Okay. 7.867. Okay, like this. It's correct. Okay. So those are two examples about the induced magnetic force on the long straight couple wire. But now we will consider magnetic force due to two conductors like this. Okay, we have the long straight couple wire lying here, and you have another conductor which is not far from each other. They are separated by the distance r here. Both will have current flowing. Okay, maybe they are not in the same amount, I prime and I. And with this one, according to the Ampere's law or the Biot-Savart law, right? According to the right-hand rule, there will be induced magnetic field rotating like this. Okay, and at this point, the magnetic flux will go in this way, right? And once you have the vector L, the current moving in this way, you rotate your 4 fingers from vector L to vector B, you're going to get the force that is pointing down. Okay, the force that is pointing down. In the same way, this one, the current is flowing this way, and this one will generate the induced magnetic force, and it hits this one pointing this direction. If you rotate from the vector L to vector B, right, you're gonna get also the force induced in this way. Okay. Okay. From another figure that's taken from another book. This one, when the two connectors are arranged in the same way in parallel configuration, the induced magnetic field is gonna point out of this. This is the induced magnetic field caused by the second conductor L2 or I2 here. Okay, if the current are not in the same amount, okay, the currents don't have the same magnitude, I1, I2. Okay, I1 may not be different from I2. The currents, the induced magnetic field will point in this way. If we rotate our four fingers from vector L this direction to vector B, right, which is 90 degrees from each other, you're gonna get the force that is directed into to another conductor. Okay. The force here could be computed from F1 I1 LB2. Okay, because this is the induced magnetic field from the second line, from the second conductor. It's gonna be B from the 2 with subscript 2. But I1 is the current that flows itself in the first conductor. It's denoted by the subscript 1. The force number 1, that is the force induced on the first conductor, is I1 LB2. Okay, it's clear, B2, because it is the magnetic field from the second conductor. And from the Biot-Savart law, how strength is the magnetic field, which is at the distance d from the center of the conductor. We apply the Biot-Savart law mu0 I 2 pi d into 41. You get this expression mu0 I1 I2 L and 2 pi d. So the force depends on the current in the first conductor and also in the second conductor. It depends also on the length of the conductor that you observe, and it depends on the distance. If you are far away, you will get weaker magnetic field. Okay, now we get the force on the second conductor too. Okay, this one we generate magnetic field. We could compute the magnitude of the induced force on the second conductor. Okay, which is mu0 I1 I2 times L divided by 2 pi d. Okay, and what you can see is that F1 and F2 will be the same. Okay, because the Newton's law say that the reaction force will be equal to action force, right? So F1 is the action force, F2 is the reaction force, so both will be the same in terms of magnitude. Okay. Figure 47, 48, 49 will give you some more idea, but in 50 they will gonna this figure will summarize everything to you. If you have only a single conductor right here, there will be nothing. There will be no force, but there will be induced magnetic field. Okay, because you let the current flow in this way. If you have the two conductors laying in parallel like this, and you let the current flow in the same direction, you will get the attractive force. Okay, the force that try to bring all these two conductors to stay together. And if you let the current flow in the opposite direction with the same amount, with the same magnitude, okay, this one is going up, this one is going down, the force will change itself from attractive force to be repulsive force. Okay, the force that try to keep this one away from another one, the force that try to keep the second conductor away from the first conductor. All right, now let's consider the first example about two wires magnetic force on two conductors. If you have two wires and each conductor has the weight per unit length they didn't provide the weight. Okay, they provide only weight per unit length 1 times 10 to negative 4 Newton per meter. These are parallel in one directly above other. So let's say we have the first conductor above here. We have another conductor, that's the second conductor below there. And if the current flow in the opposite direction but with equal magnitude, let's say this one flow like this and this one flow in the opposite way. Okay, with the same amount I, and the wire are 0.1 apart. Okay, and the summation of the force gravitational from the upper right is 0. So of course the upper connector would have their own weights, right? But there will be also induced magnetic force pointing up. Okay, in the equilibrium state, summation of F should remain 0. So this force and this force should remain the same, right? So the question is, find the current in the Y. So what is I in this scenario? Yes, from this expression, F mu 0 I L divided by 2 pi d, you can see that the current เดี๋ยวครับทำไมมันเป็นอย่างนี้ okay, the current in the first conductor is I1. It's equal to the current in the second conductor in magnitude. Okay, let's say it's equal to I, and we want to find I. F1 will be mu 0 IIL, mu 0 I1 I2L divided by 2 pi d. Okay, and I1 is equal to I2, which is I, right? So we're gonna get mu 0 I square L divided by 2 pi d. But what we want to find is I, right? So we move 2 pi d to the left, mu 0 to the left, L to the left. So we're gonna get I square will be 2 pi df divided by mu 0. But f could be computed from the equilibrium state, right? Summation of f is 0. So Newton's law says summation of f is 0 in the equilibrium state. It means magnetic force will be W, and W is the weight, right, which is mg, m of conductor times gravitational acceleration on Earth. The mass of this conductor, how could you find that? What they say is, okay, don't worry about it. Don't worry about it. Oh, yeah. Mu 0 L to here. Okay, L. Sorry for that. Okay, don't worry, but we would not go into detail to the MG because they don't provide. What they provide is only W per L. Okay, because F is W, so I square will be 2 pi d W by mu 0 and L. Okay, like this. And they have provided the value for W per L, weight per length, right? 2 pi is 2 pi. D is the separation distance, which is 0.1 meter. W per L is 10 to the negative 4, like this. Okay, let's close the calculator. 10 to negative 4 divided by the constant, right? Magnetic permeability in vacuum. 4 pi times 10 to negative 7. You can cancel number 2 here, right? It's going to be 0.05 times 10 to negative 4. And 10 negative 7. So finally, it's going to be 3, right? 1,000. So it's 100. Okay, but this is not I. It's I square, right? If you take the square root, I is going to be square root of 100, so it's going to be 10 ampere. I'm not sure whether it's correct or not. Oh no. 4 pi, 2 pi. 1,000. Oh, it's only 10. My God. Stupid. Right. Oh, 5. My God. 1,050 square root of 50. Right. Square root of 50. $707, is that correct? Yes. Okay. Square root of 10, and that's 7.07. Okay, approximately ampere. It's not this one. Okay, 0.07 ampere. For the first example about force on two parallel conductors. Okay, let's consider the next example. Two-thread parallel superconducting cable. What does that mean? There is no resistance. So it means superconducting. R is 0. Okay. Resistance is 0 ohm. Okay. 4.5 millimeter apart. Okay, between centers. Carry equal currents of 15,000 in the opposite direction. Find the magnitude and reduction of force per unit length. Except one conductor on another. So let's draw. If you have the first conductor like this, you have another conductor like this. The current flow in the opposite direction. 15,000 ampere. 15,000 ampere. Okay. And distance is only 4.5 millimeter. Magnitude and the direction, right? So if you let the current flow in the opposite way, the forces will be repulsive force. Okay, the force will try to keep this one away from another one. The force will be in this direction to keep the second conductor away from the first one. Okay, let's consider the magnitude, right? Oh, they draw it here. The length that they want to consider. No. Okay, find the force per unit length. Okay, this one. Force per unit length means F by L, right? What is that then? From the general expression, F is mu0, I1, I2, right? But I will be the same. I1 is I2 is I, and L is the length divided by 2 pi d, right? Resistance is R. Okay. If we express it for L, right, it's going to be F by L will be mu0 I squared divided by 2 pi resistance there, 2 pi d. So F per L will be mu0, which is 4 pi times 10 to the negative 7. And I square is 15,000 square. And divided by 2 pi. Distance is 4.5 millimeter. This one is 4.5 times 10 to negative 3 millimeter. So you're gonna get 2, right? It's 30 by 4.5, 10 to negative 7, 10 to 6, and here 10 to 3. So it's gonna be 9, right? 100. So it's 30, 100. Oh, no. 2 only. 2, 0 divided by 4.5. And 6666. Oh my god, is that correct? No. 2 pi d. I didn't calculate it properly, my god. 15,000 to 6, 9 to 100. 30. Right. Two pi d millimeter. 9. 30. 4.5. Oh my god, what happened? Madonna. F per L equal to 4 times pi times 1 e minus 7, right? Mu0 I square and times I, which is 15,000 square divided by 2 pi d 2 times pi times d, which is 4.5 millimeter. E minus 3. Just 10,000. I don't understand why I get this one. Oh, 15 twice. 15 too, my God, I forget 15. This is 15, not 30. My God. 2 and 15 square, right? It's 450. 450 divided by 4.5 and times 10 to 9 to right. So it's going to be 100 times 10 to 2. Right? It's 1,000, 10,000. Okay, 10 to 4 Newton per meter. Okay, 10,000, which is the same thing here. Yes. So consider it in reality. So should we be concerned about the mechanical strength of these wires? So what is that then? It means in 1 meter, if this is the fix and this is the line, there will be like the car, okay, in 1 meter, 1 meter only, like the car that has its own weight around 1 ton, okay, 10 to 3 kilogram. In 1 meter, is it possible? เอารถยนต์ที่มันหนักประมาณ1ตันครับมาวางบนเส้นลวดที่ยาว1เมตรจะเป็นไงเส้นลวดก็ขาดมันลดมันรองรับน้ำหนักไม่ได้ so it's impossible. Okay, it's impossible. So this will not be valid in reality. Okay. Let's move to the next one. Okay, talk on a current through and solenoid. If you have the conductor that is oriented like this, it's not long straight copper wire, it's a little bit more complicated. Okay, it's made by human. Like this in this rectangle formula, rectangle shape. Okay, current flow in this way, right? And here is the size of A, size of B. If there is magnetic field pointing or directed to the right, okay, from left to right like this, and of course you're gonna see that this is L vector. Oh. This is vector L. This is also vector L, right? And vector B is like this. Vector B is like this. If you rotate your vector from L to B, this one will be magnetic force pointing to us, right? Direction of the induced force is going to point to us. The induced magnetic force is going to point downward into this plane. So in the side view, you can see this is up and this is down, right? Upward force, downward force, right? And the moment is force, okay, force times distance. Right. And torque is another word as moment. In this one, you have, if this is the pivot rotation point, this is rotating point. Moment from the left one, which try to keep it moving around, right? Try to move it around. This one, move it around in the same way. Okay. Moment will be moment 1 plus moment 2. Moment 1 is this one. F1 times left hand side distance is F1 times A by 2 plus this one. Okay. F2 A by 2. But F1 and but F1 is equal to F2 in magnitude, right? So let's say it's equal to F. So magnetic moment will be F times A. Okay, A is the distance here in this part. But F, as you know, F can be computed by what? F could be found from mu0, right? ILB, right? F could be computed from ILB, right? F here, this side is F2 is IL. The length of the conductor at this part is B, right? B, small b, IBB. F1 here on the left hand side, again the same. IB ผมไปกดโดนอะไรครับหรือว่ามันถึงแบบทำเป็นเส้นๆอย่างนี้ให้นะครับผมทำอะไรผิดหรือเปล่า Okay, FIBB. Okay, it's the same thing. F1, F2 is F, so M, which is the torque, actually, IBB times A. But as you know, B and A is the area, right? The area right here. B times A is the area. Area is the B times A. Let's say it's the capital A. So this one, the torque will be IAB. Yep. What do you want to say? BIAB. Okay. Or you want to say E bar, like this. Whatever sequence of these 3 variables. Okay. Just memorize this thing for torque. But what happens if we arrange this conductor at the angle theta? Okay, the normal vector of this this is a side view of this one. Normal vector of this area is directed like this. Is situated at angle theta from the vector B. Okay, like this. So you can see that we can project this one, right, to the normal one, right, to the normal component. No, you can project this one, right. We can project this vector right to this component. The distance here is going to be a side. It's not a anymore. Okay. This angle phi, right? This angle phi. So this angle will be also theta, right? And if we draw it again, this one is a by 2. This one is going to be, this is theta, right? A by 2 psi theta, right? Okay, the distance here is a by 2 psi theta. So instead of a by 2, we're going to use a by 2 psi theta. So everything will start from here. IBBA psi theta. Right, torque is IBBA psi theta. And yes, torque will become BR psi theta finally, because B and A is the cross-sectional area, is the area. All right, yeah, BR psi theta. But one important thing is that the property of that conductor is known as the magnetic moment, which is the product between current and cross-sectional area. And the unit of the magnetic moment is ampere and square meter, like this. Okay. And the maximum value, if you take the maximum value of psi theta, as you know, the psi would have a shape like this. We start from 0, right? This is psi theta, and here this axis is theta. Okay, the maximum value you start here is 0. The maximum value is this one, which is theta is 90 degrees. Okay, theta is 90 degrees. The maximum value, which is number 1. Okay, this is number 1. All right. Maximum value of psi theta is number 1, so we max this one. It's going to be psi 90 degrees, number 1. Okay, this is equal to 1. So the result torque max, okay, it's not typical torque. It's torque max. The maximum value of the torque is BR, okay, without psi theta, because the maximum value of psi theta is number 1. In this figure, it's a little bit complicated, but it's in the same way. If we have the magnetic flux pointing upward like this, okay, the blue one, this is the vector of magnetic field lines. And if we let the current flow in this way, it's like a counterclockwise direction, okay? Seems how like counterclockwise direction. And at this location, vector L is like this, B is like this. You turn your 4 fingers from L to B, you're gonna get the induced force direction in this way. And at this location, vector L is like this, right? From this point to this point, and the magnetic field is up, right? L to B, you rotate your 4 finger like this. Your thumb direction is gonna give you the induced force in this way. And okay, the same. This is the vector L. L to B, you get the induced force direction to the left. This is vector L to vector B, right? L to B, you use your right hand rotating your 4 fingers, you will get the induced force in this way. This force and this force will cancel each other. Okay, there is no translation or movement of this conductor, but this one is gonna move this one to this part to the right, this part to the left, so it's gonna rotate this one, but this conductor will not move at all because the balance of these two forces. Okay, so torque Bn could be represented as phi, okay, because they use phi in this scenario. Okay, whether it's theta or phi, okay, it's Br psi phi or psi theta. Okay, so the maximum value will happen once the phi is 90 degrees. Okay, the normal vector is done or is situated at 90 degrees to the vector of the magnetic field. Okay, this is the maximum torque moment. Torque max will be the same thing, Br psi 90 BIA. All right, and the torque will not exceed if the conductor locates like this, because the L is this way, right? L to B is gonna point, the force is gonna point to this direction. L in this way, right? L to B, the force will be in this direction. Okay, they will cancel each other because it lies in the same plate. And this is the L this direction, right? To B, you get the force in this direction. L to B, you will get the force in this direction. Oh, sorry, L to B, you get the force in this way. This one, this will cancel with this force. Okay, and this is the moment that we have minimal force. Okay, zero force actually. Top mean is 0. And if you have many rounds of conductor, right, this is like spring and so on, the torque will be n times of the original one. Okay, it will be n times more. Okay, you just add it. The formula is going to be Bn psi phi, okay, or Bn psi theta. But the important thing is known here as a total magnetic moment. Okay, that includes all terms. Okay, Ia and En, as the mu n is the total magnetic moment. Okay, let's consider this example. We have a circular coil with average radius of 0.05 meter and 30 turns. Okay, lie in horizontal plane. It carries the currents of, okay, let's say it's like this, 30 rounds. Okay, 30 turns. Okay, and the current get into this and get out of this. It's 5 ampere. It's rotated in the counterclockwise direction. Okay, and this is the top view. Okay, view above. There's magnetic field 1.2 Tesla from left to right, like this. This is B, and the absolute value of B is 1.2 Tesla. Find the magnetic moment and the torque on the coil. Okay, of course, your L vector is going to be here, and this is the vector B, right? L to B, L to B, right? It's going to push this one down, right? L to B. It's going to push this one down. L. It's going to put this one up. Okay, lift this one up. Push this one down. Okay. Yeah, it's going to rotate like this. find the magnetic moment and the torque on the coil. Okay, we are running out of time right now. Let me complete this problem. The magnetic moment is the mu n is n, right? I-A-N. So the current is 5. A is the cross-sectional area. Pi of the radius 0.05 meters square. And n is the number of turns, which is 30 turns. Okay, just compute it. Okay, 5 times pi times 0.05 square times 30, 1178 approximately. 1178. The unit is ampere square meter. Is that correct? 1178. Yes, here 1178. All right. View total. So the next one is the torque, right? So torque is the product beer, right? BN psi phi, right? But at this moment, the normal vector of the plane of this circular loop is situated 90 degrees to the vector B. So phi is 90 degrees, so we don't need to worry about it. So B is 1.2 Tesla times the 5 times pi times 0.05 square and 30 and psi of 90 degrees. So it's number 1 actually. So we don't have to worry about it. Just multiply further by 1/2. 1.2, sorry. 1.2. We get 1414 approximately. 1.414. The unit of the torque is like moment, right? It's Newton, F, and distance is Newton meter. And the last question is, what way does the coil tend to rotate? And as you know, here is a pushing force. This is the lifting force, right? In the side view, of that coil. This is the coil, right? This is the pushing force. This is the lifting force. So this is the side view, okay? The coil will rotate like this. Okay, it's like a clockwise direction, okay? Clockwise direction, or the left moving up, and right moving down. Upward and downward. All right, and that's it for this problem. Thank you very much. นะครับอย่าลืมนะครับเราสอบถึงเรื่อง electric generator นะครับขอรบกวนคุณนะครับไปดูที่วิดีโอนะครับวันนี้อาจจะไม่ต้องดู18 19แล้วมั้งครับอาจจะเริ่ม20เลยก็ได้มั้งครับแล้วก็ดูไปจนถึงอันที่6นะครับเขียนมา26นะครับก็ข้อสอบออกถึงเรื่อง electric generator นะครับโอเค thank you very much see you after the midterm exam okay good luck with the midterm exam if you cannot get something like a 10, okay, you have another chance to get to if you fail, right, you can have next chance to increase your mark or your midterm exam score. บ๊ายบายครับสวัสดีครับโอเค vaccine 19 Akila 15 Okay.